Hey, good evening and welcome back to AP Stats Notes Online. I want to continue talking about describing location in a distribution. Last night we talked about percentiles. Again, percentiles correspond to the percent of observations that are less than that, and that's exactly the definition of a median, Q1 and Q3. And so it makes sense that percentiles are kind of tied to those measures, and therefore it probably makes sense that we would use percentile to describe location in a skewed distribution, but we can certainly do it for symmetric distributions as well, or roughly symmetric distributions. We were going through yesterday about z-scores. A z-score is tied to the mean and standard deviation. And bottom line, again, definition is of a z-score is how many standard deviations from the mean the observation falls, right? It also gives us a sense of direction. And so quickly, you wrote this in last night, even though your homework didn't get into z-scores. We probably could have saved that for tonight, but that's okay. The standardized value. So how do you get that standardized value? How many standard deviations from the mean? Well, from that sentence alone, you can kind of get a glimpse into the equation, right? So I got to find out how far a particular individual is from the mean, so it means subtract, and then to figure out how many standard deviations away it is. Some of you guys, through the activity of the arm length that we did with the dot plot, started to sort of figure out, well, to find out how many standard deviations away, I just divide by whatever the standard deviation is. And so there's your calculation for a z-score. And it's also considered, again, just as a quick reminder, as a standardized value. Standardized test scores, standardized anything should refer to a z-score. And therefore where you are in that distribution in terms of where you are from the mean. So z-scores definitely have a lot of meaning with roughly symmetric or symmetric distributions. Again, mean and standard deviation are those resistant or non-resistant measures. Think about that for a second, and hopefully you're thinking about the fact that mean and standard deviation are non-resistant measures and therefore can be affected. So your z-score calculation can be affected by skewness or outliers, and so we want to be careful about using z-scores for those situations. We certainly could, don't know how much meaning they would have. Okay, and then last night's notes, we talked about Jenny again, going back to her 86% on her stats test, where the class mean. So, again, the point here is, should you be happy with an 86? 86 in our world is a B. And should you be happy about that or not? Well, it's all relative to the mean, as it sort of came out in our discussion, right? So the class mean was an 80. The standard deviation was 6.07. And the standard deviation is important too, right? I mean, should you be happy that you scored 6 percentage points higher than the mean on your AP Stats test? Well, yeah, I suppose, unless your standard deviation was really, really big, and that basically means that you're not that far from the mean, so you're average. Do you want to be average, or do you want to be above average? Or do you want to be excellent? And so, it all kind of goes into those questions. And so we talked about yesterday, the way we find out her standardized test score is we take her score, find out how far from the mean it is, so subtract it from the mean, and then find out how many standard deviations away. So we divide that by the standard deviation, 6.07. So she is almost a full standard deviation above the mean. Direction, don't forget direction. Positive means above the mean, negative means below the mean, and that has everything to do with the fact that we're subtracting in the order that we're subtracting in the numerator. Okay? And we'll find out if one standard deviation away is good or not that far away or whatever. That'll all come when we start talking about normal curves and things like that. So, okay. Another use for z-scores, okay, is to try to compare an individual or a couple of individuals in different distributions, right? Like I said in our arm-length dot plot, right? Are you short-armed or long-armed, and would your answer change if I put, instead of putting you in a distribution of classmates, I put you in a distribution of NBA basketball players, right? And so we'd want to compare some individuals in two different distributions in a more I guess more relevant to you example of this is, again, on page 91, we have this example that talks about Jenny again. So she got her stats test back and she got an 86, where the mean was an 80, and the standard deviation was 6.07. And she scored an 82 on her chemistry test. So 86 versus 82. Should she be happy about her stats test, or should she be should she be happier about her stats grade or happier about her chemistry grade? And at raw score alone, 86 and 82, you might think the stats test. That went better for her. Okay? Well, the mean and the standard deviation for her chemistry test was 76 and 4, respectively. So, in fact, which test did Jenny perform better relative to the rest of her class? Well, in order to find that out, we need to find out how far away from the mean she actually is in either class, right? So, easy enough to figure that out. For her AP Stats test. And we've already done this calculation, but I'll show it again. To find your z-score, her position in that distribution, we take her score minus the mean, divided by the standard deviation, and again, that value was 0.99. So she's almost one standard deviation above the mean. In her AP Chem test, her z-score, well, she scored an 82. The mean was 76. So how far away from the mean was she? Well, she was 6 percentage points again, right? Away from the mean. However, the standard deviation for this test was 4. So a little less spread. The scores were sort of packed together a little bit more, right? Which means that here, her z-score was what? 6 divided by 4. And divide that out, and I'm pretty sure you get 1.5, and you do. So her z-score here is 1.5. So as an interpretation for these two scores, right? Jenny scored almost one standard deviation. Remember that z-scores are always measured in standard deviations above the mean. Right? Here, Jenny scored 1.5 times, 1.5 times. Sorry, not times. Jenny scored 1.5 standard deviations. Jenny scored 1.5 standard deviations above or better than the mean. Okay, so which one did she perform? Did she actually perform better on? What was her AP Chem test? Right, she was higher. She scored higher relative to the rest of the class on that test. Okay, so z-scores give you an idea of how to compare in a couple of different distributions. Okay, and we'll actually use z-scores a lot. Percentiles a little bit. We'll keep coming back to percentiles some, but what you're going to find as we have conversations in this class is that statistics works a lot better when we can tie in probability and we can predict and tie in probability a lot more with symmetric distributions. And so mean and standard deviation calculations and anything that uses mean and standard deviation to calculate, like a z-score, are going to have a little bit more meaning for us. So we'll definitely continue talking about z-scores and the fact that positive means above the mean, negative means below the mean. And z-scores are measured in standard deviations. Okay, so this is kind of a big deal for us. Make sure that you definitely understand z-scores. Okay, and we'll zip through this. Okay, check everything on page 91. Again, work through that. Take a couple minutes to work through that. If you want to do it now, you can pause the video and give it a shot, and then we'll talk about it when we come back together in class tomorrow. Okay, and find out what your answers are there. All right. The next thing I want to talk about is the next thing that your activity, your arm length activity walked you through was transforming data. What happens when we start transforming our data? And to help see this, we'll do this in a generic sense first. Okay, so this is why you needed this handout. Remember, this was your quantitative data handout where we started talking about all the different graphs and how to describe them and all that kind of stuff. On the very back page we skipped because it's talking about transforming your data. What happens if you take your data and multiply it by a constant or divide? And then what happens to your data if you add or subtract a constant to all of your data points? Okay? So in a generic sense, we can do this first just to kind of get a pattern, establish a pattern here. So what I would like for you to do, and so again, what we're going to talk about is this is what your linear transformation might look like. So all of your data points, all of your x's, we're either going to multiply by a constant or divide, or add or subtract a constant, or we might do both at the same time. Okay? So what are our new data points, and how does that affect our numerical summaries? So do this pretty easily. If you will put these into a list, right? 3, 4, 6, 8, 12, 15, and 20. Because when you have a list, you can start to get all of these numerical values very, very quickly, right? So mine's in list 4. You can put yours wherever you want. So remember, we go to stat, calc, one variable stats, and I need list 4. I don't need a frequency. Oops. Calc. I need list 4. I do not need a frequency list. And I want to calculate all of my one variable stats. Okay? And so when I do, I can write down these values. Let's see. The median, I'm going to have to arrow down for the median, and you can't really see that because of this glare. Can I get rid of this glare? Nope. No, that does it. That's a little bit better. So I'm going to arrow down to median. The median is 8. The mean, I'm going to arrow back up, is 9.7. The range, remember range is max minus min. The max is 20, the min is 3, so my range is 17. IQR is Q3 minus Q1, so this is 15 minus 4 or 11. And I'll write these up here where they're coming from. So 15 minus 4. Standard deviation is going to be 6.2. And then the variance, I need to square standard deviation. I'll show you this function as well. If you don't have to quit out of this, if you go to VARs, this button down here, VARs, and arrow down to statistics, okay, then you can grab the S sub x that you just calculated. And then you can square it. And so it'll take that entire decimal and square it for you instead of having to have a squared, a rounded squared number in there. A little less accurate that way. Okay? So there's your original data. Now, what happens if we add 4 to each value in the original data and complete the table. Okay, let's find out. Let's go back into my list. And I want to add 4 to all of these guys. So I'm going to arrow over to L5, arrow up to the title of L5. And I'm going to tell it to take list 4, so type in second 4 for list 4, and I'm going to add 4 to each of those. And there, it populates all those values, so you can see 17 to 24. Now, to find out my values, I'll go back to stat, calc, one variable stat. Now I'm in list 5. You can be in any list you want. Okay, and so we hit list 5 and we hit calculate, and voila, there are our numbers. So, our new median, we arrow down, is 12. Our new mean, we arrow back up, is 13.7. Our new range, our max minus min, is going to be 24 minus 7, which is still 17. Our IQR is going to be Q3 minus Q1, which is 19 minus 8, which is now 11. Our standard deviation is 6.2. And then again, our variance, we can go to VARs. Not quite seeing that. Go to VARs. Down to statistics. Go grab our S sub x. Square it. And we get 38.9. Okay? Now take a look. What happened? Remember, these are our measures of center. These are our measures of spread. Our measures of center. The actual values of the center did increase by a factor of 4. We added 4 to them, right? Don't want to call it a factor of 4, but we added 4 to them, right? Look at our range, our IQR, our standard deviation, our variance. They did not change. Okay? There, if you want to compare them. They did not change. Okay? So, apparently adding 4 to all of our data points will only affect the measure of center and not necessarily the measures of spread. All right? All right, well, what if we decided to multiply each value in the original data by 3? Okay? Let's go do that. Let's go take our list and edit it, right? So list 5 again. I'm going to use list 5 to take list 4 and multiply it by 3. Okay, when we do that, there's our new list and our new values that correspond to the values up there. All right, so we got our new list. Let's go do our calculations, right? So stat, calc, one variable stats. I'm on list 5 again. I'm going to calculate that stuff, and here's what I got. Okay, so the median, I've got to arrow down, the median is 24. The mean is 29.1. The range is going to be your max, which is 60, minus your min, which is 9, and that's going to be 51. Your IQR is going to be your Q3 minus your Q1, that's 33. Standard deviation is 18.7. And to find your variance, again, we're going to go to VARs, statistics, S sub x, and then I'm going to square that and get 350.1. Okay, so let's analyze now. Okay, so if I take all of my data points and multiply them by 3, then what happened to median? Well, it went up by a factor of 3. And your mean also went up by a factor of 3. Your range, well, your minimum and your maximum values did change. They did increase by a factor of 3. But what's also interesting is so did the actual difference. Right now, the max and the min are farther apart from each other. And so our range increased also. How much? Well, if you take 51 divided by 3, you get 17. So apparently it went by a factor of 3. IQR is the same. The Q3 and Q1 changed by a factor of 3, but also the distance apart went up by a factor of 3. Standard deviation was the same thing. 38.9, if I multiply that by 3, I get not 350.1. right? The 38.9 is your original variance. That didn't happen. Well, how much did it go up by? If I compare 350.1 to 38.9, it actually went up by a factor of 9, which hopefully makes some sense. Remember that variance is standard deviation squared. Well, if my standard deviation is going to increase by a factor of 3, then my variance is going to actually end up increasing by a factor of 9. 3 squared and s sub x squared will give me my new variance. So variance actually goes up by the square of the constant that I'm multiplying by. What's the moral of all this story? The moral of all this is that if you know you're transforming your data by a constant, then you don't have to actually go through and transform your data points. You can just take your median or your mean or your range or your IQR or whatever that you need and adjust it accordingly. Okay? And so far it looks like median, mean, range, IQR, everything is affected by multiplying by 3. Not true when you're adding by 4. Only the centers moved. Okay? We can use this to predict the change. Like I said, we don't have to type in. So if I'm going to multiply all of my data points by 2 and then add 3 to them, I could go into my list and do that to my data set. I could. Or I can use some pattern recognition here. What's going to happen to median? Well, median changed by adding and it changed by multiplying. So my original median is 8. My new median is going to be 8 times 2, which is 16, plus 3, which is 19. My new mean, or my old mean was 9.7. So my new mean, it means affected by the adding and by the multiplying. So 9.7 times 2 is 19.4, plus 3 should be 22.4. Range was not affected by adding, but was by multiplying. So I'm going to take my range and multiply it by 2, which is 34. Same thing with IQR, right? So I'm going to take my 11 and multiply it by 2 and get 22. Same thing for my standard deviation. No change in adding, but change in multiplying. So I'm going to get 18.6. Oops, nope, sorry. This is multiplied by 2, so this is going to be 12.4. Variance, no change in adding, change in multiplying, but by the square factor, right? So it's going to take 4 times 38.9, which is going to be 155.6. So that's how it should change. You want to check those? We can do that. We go into your list. Again, I'm going to arrow up to the top of L5, and I'm going to tell L5 to please take L4 times 2 and then add 3 to it. Oops. Then add 3 to it. When I do, boom, I get all of these data points in my list now. Let's go do our statistics. Stat, calc, one variable stat. Do it on list 5, please, and hit calculate, and let's see what happened. Is the median 19? Yes, it is. Is the mean 22.4? Yes, it is. Is the range 34? Well, the range goes from 43 to 9. That is definitely 34. Is the IQR 22? Well, IQR goes from 33 to 11. Yes, it definitely is. Is the standard deviation 12.4? Yes, it is. And my guess is when we go to VARs, statistics, pull out S sub x, and square it, we get, looky there, 155.6. Okay? So, moral of the story. Moral of the story is there's a pattern to this, and we can develop some rules. Right? If I'm going to take all of my data points, all of my x's, all of my individuals, and multiply them by a constant and or add a constant to them, or of course this works for division and subtraction the way that you should be able to figure out that it would, then I can predictably guess the new median, the new measures of center and spread. Right? So from up here, our new rules are this. To get the new median, I'm going to take old median and multiply it by B and then add A. Okay? New mean. I'm going to take old mean, multiply it by b, because it was affected by multiplying, and add a, because it was affected by adding. Okay, you can go back up to the table and see that. The new range, I'm going to take the old range and multiply it by b and add a. Well, if you go back up, range was not affected by adding. So no, we're not going to add a. IQR new is going to be IQR old, and then multiply it by b, and again, no adding, because it did not change when you added the constant. Standard deviation. We're going to take standard deviation old, multiply it by b, but do not add anything. Variance, we're going to take variance old, multiply it by b, not quite. We're going to multiply it by b squared. And again, that comes from the fact that we have to square the standard deviation to get to the variance, but not add a. Now, sometimes we have to add the constant first before we multiply by the constant. I'll show you why in just a second. But these are the rules. The measures of center are affected by multiplying and by adding. The measures of spread are only affected by multiplying. Okay, so we can use these rules to kind of go backwards a little bit too. So suppose a teacher gave us a test for which the mean was 70 and the standard deviation was 21. He wants to apply a linear transformation. This guy right here was a linear transformation to scale the grades so that the mean is actually 82 and the standard deviation is 7. Make his numbers look nice and pretty. So go find A and B. All right, well, we know that in order to find x bar new, we have to take x bar old, multiply it by b, and add a to it. In order to find standard deviation new, I have to take standard deviation old and just multiply by b. I don't have to add a. Now it becomes sort of a system of equations to solve. Standard deviation new, I want it to be 7. The old standard deviation is 21. So in order to find b, I just simply divide both sides by 21. Now it becomes an algebra problem. Yay, algebra. Wish I was there again, right? That's what you guys are thinking. All right. Now that we know b, we can plug b in up over here. The new mean we want to be 82. The old mean was 70. I'm going to plug in for b and find out what a has to be. Right? So if I take 82, if I take 70 times 1/3, I get 23.3 repeating. And then I'm going to subtract 23.3 repeating from both sides. And so A ends up being 58.7. So if I want my new mean to be 82 and my new standard deviation to be 7, then I'm going to take everybody's test score, multiply it by 1/3 or divide by 3, and then add 58.7 to it. Okay? So that's one way you can transform your data. And so that, this kind of works into some rules that you can put. So you have this sheet, right? We can transfer these rules over to your slides. You can have them all in the same place, have them in a couple of places, and that would be good. Okay? Transform and converts the original observations from the original units of measurement to another scale. Right? Sometimes we want to change units, like we did with the arm length, right? The question for your arm length was, if I wanted to report all of your measurements in centimeters instead of inches, then I have to multiply all of your data points by 2.54. What would happen to your measures of center and spread? Okay? Well, one thing that we did not address in this note packet is shape. What happens to shape and positioning, right? Well, let's think about this common sense-wise first, right? If you had the shortest arms in the class, and then we multiplied all of those measurements from inches to get from inches to centimeters, so we multiply them all by 2.54. Are you all of a sudden going to have the longest arms in class, or even the middle length arms in class? No, you're still going to have the shortest arms in class. Just because we change units doesn't change how long your arms get, okay? Because we're transforming everybody's, right? So position shouldn't change. Q1 and Q3 will still be the same individual. Just the value of Q1 and Q3 will change, okay? So what about the entire shape of the graph? Well, I still have, and I'm pretty sure this is seventh periods arm lengths and their frequency list, right? And I have created a histogram based on those. Okay, those are all in inches. There's your histogram. Roughly symmetric, right? Bars are going up, 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 and then drop down a little bit. So remember that graph, because now I'm going to go into my list, and I'm going to transform all of these arm lengths from inches to centimeters by multiplying it by 2.54. Boom, they're all in centimeters. Now, if I decide to graph that, oh, can't see it. Zoom stat, right? This is not the same scale, so I'm going to have to try to figure out the scale here. Well, the original scale, I might be in trouble here, went from 20, and so 20 times 2.54, can I do that in here? I bet not. Oh yeah, it will. To, I'm pretty sure 35. And my scale was by threes, so I'm still going to take that 3 times 2.54, and that, yeah, I'm sure my scales are off. That was not very good at all. What you should have seen here was that the shape isn't going to change, right? And it shouldn't. The scale might get a little bit larger, but because the positioning won't change, neither will the shape of a distribution, okay? And we're going to use that quite a bit going forward. I did that on the fly and it didn't work out, and I apologize. Maybe I can take a look at it and show you guys a little bit better idea tomorrow, okay? Transformations can affect the shape, center, and spread of a distribution. Effect of adding a constant, we just saw, right? Adding the same number, either positive, 0, or negative, to each observation adds that same number to the measure of center and location. So mean, median, quartiles, and percentiles, okay? But does not change the shape of the distribution or measures of spread. Okay, like I said, the location, don't get confused by that. Your median and quartiles, the value of them will change, as well as your percentiles, but not which individual. Okay, there's a difference between those two. Okay, and so here's an example on page 93 that walks you through this. That gives you a better idea of transforming. I think this was trying to guess how wide the room is in meters. You know, you can read that example and figure out where the dot plots came from. But when they plotted these, you can see that everything just picks up. And when we added a value to them or subtracted, then we found that, anyway, you read through the example, you can see that the mean changed, the median changed, the quartiles changed, IQR did not, range did not, standard deviation did not, and shape did not. And this is a better example of how shape didn't change, okay? Next, your rules for multiplying or dividing by the same number, positive, negative, or 0. Multiplies the center and location by B. Multiplies the measure of spread by absolute value of B. Remember, your spread can't be negative. It doesn't make any sense, right? But still does not change the shape of the distribution. Okay? Again, page 95 picks up the same example, shows you what happens if our guess and width of the room goes from meters to feet. Okay? You can see that the actual measures of the center, median and mean changed, standard deviation changed, everything changed except for the shape. Now, they're a little bit more spread out, but you're still going to call this, what, I don't know, possibly skewed right, maybe if you leave these out, maybe roughly symmetric, but it's the same shape, okay? So again, check your understanding on page 97. work that one out as well, and we'll come back and talk about those at the beginning of class tomorrow. All right? And then tomorrow night, we'll come back in and do some notes for the weekend talking about density curves. But that's it for tonight. Homework's in the text, and we'll see you in class tomorrow.